This time I'm not going to talk too fast as I usually do because of the time pressure. Okay, I think we can start with writing a title. So as you notice from the lectures, this module, the second module of your course is especially difficult. I'm not exaggerating, it's really been difficult for all the students in all my career. This vector analysis, vector fields, double and triple integrals, and so on. So many things. And they all need to be covered in only like 4 tutorials. And after that, you are going to have another test. So be especially attentive. Try to work hard on the assignments given in tutorials because it's really tough. It's much tougher than the previous one. The previous one was just a piece of cake compared to this model. Yeah, I'm being absolutely honest. Okay, so let's start discussing it little by little. As I said before, I'm going to record this tutorial, and that is why it will be very, very long, maybe 1 hour and a half, maybe even more. And that is why I'm not going to speak very fast this time. Okay, so as usual, I split these tutorial topics into several subtopics. So the first subtopic will be nabla operator. Let's discuss this nabla operator and how to deal with it, and how to overcome your fear of this nabla operator. Of course, you remember the notation. It was capital Greek letter nabla, which has a symbolic vector with very weird components: d over dx, d over dy, d over dz. So this was the definition of nabla vector. But you know, I prefer to put an arrow here to emphasize the fact that it is a vector. It's better to have arrow here. Again, and what is so weird about the components of this vector? The weird thing is that you are used to having some function here, df over dx, or d is something else over dx. But here you don't have anything. You just have a blank space here. This blank space can be perceived as a placeholder, because right after you applied this nabla vector to some function, these blank spaces get filled up, and these guys will look like normal partial derivatives. Okay, and so now maybe it's interesting for you why is so much emphasis being put on this nabla operator. What's so good about it? What's so wonderful about it? The thing is, it's just a very convenient notation. Instead of writing very long and bulky formulas, you can use just this nabla operator to make things look very beautiful and concise and short. So let's demonstrate it by some examples. But you know, apart from nabla vector, we will also need some function phi. Let's call it phi of 3 variables. It could be 2 variables as well. But let's just imagine that we are dealing with 3D situation, and we also will have maybe to deal with vector function with 3 components. Let's denote these components P, Q, R. This is like an introduction. Okay, and now I'll start trying to convince you that nabla operator is absolutely wonderful. So what I'm going to do, I'm splitting the page, my A4 page, into 2 columns. In the right column, I'm going to discuss ordinary vectors, just geometrical vectors. You're pretty used to them. You know everything about them, actually. And here, I'm going to build analogy to the same operation. Okay, let's recall that once we had an operation over vector, which was just multiplying vector by some constant. So A was just an ordinary vector, geometrical vector. And this symbol means that we are going to multiply it by some constant k. So this is scalar, this is vector. How did you do it? You just multiplied every component of this vector by this constant k. So k(x), the next component will be k times ay, and the last component is quite similar. So how this operation went on. It was just multiplying by scalar, multiplying the vector by scalar. What about our current topic? We are dealing with this scary nabla vector. You know what? I can write you this thing: nabla times phi. Look at this. Just I swapped the order of the terms, but it doesn't matter. Look at this. Nabla plays the role of a vector. It's because this is vector, and phi if you look at the phi, it's just a number. It's just a function, but it plays the role of number. So phi is like k. So in this case, this thing does look like this operation, like multiplying the vector, given vector nabla, by constant 5. You can imagine this. Okay, let's perform this operation. But let's just write down the vector nabla first. Again, d over dx, d over dy, and d over dz. I'm running out of space. And times 5, times this scalar 5. How do you perform this operation? Look at the right column. You need to multiply every component of this vector by phi. And in our case, it won't be exact multiplication. It will be like this phi. Phi takes the place of this placeholder, and as a result, these components look like quite normal partial derivatives now. So that's the benefit of this symbolic expression. It means that you don't need to memorize some big formulas. You need to memorize some very shorthand notation. So this is analogy to this vector operation. Okay, let's get back to normal geometric vectors again. You used to deal with so-called dot product or scalar product. Do you remember this? So for example, if you wanted to multiply two vectors as a dot product, there was a nice formula, ax times bx. So you needed to multiply the first components of both vectors, then do the same to the second component, or by, and the same to the third components, and then to add them together. Very nice formula of scalar product. And you know what? You can bump into this case here as well, just with nabla. So nabla times f, vector f. Look at this. It does look like scalar product, and it is a scalar product. So all you need to do, you need just to expand this expression. So let's substitute the coordinates, components of this vector here, components of this vector, and perform this scalar operation. Let's do it. So the first vector is our symbolic vector again, d over dx, d over dy, d over dz. And now vector f, do you remember I denoted them as p, q, r. These are functions, but p, q, r. Okay. And now we know the rule. We can look at the right column. So as a result, we'll get the first component here gets multiplied by this component, p, which is p, dp over dx plus, according to scalar product rule, the second component times the second component, and the same thing for the third component. Look at this. So we managed to figure out what was hiding behind this notation. And the last thing, even, I'm running out of space on this page. I need to switch to a new page. So this will be the third row in my table. Strange looking table. Okay. So, and of course, you still remember the cross product of two vectors. Do you remember? A times b by cross product. The rule was a little bit fancier, but still very memorable. So the first row was ijk, these basis vectors. The second vector was components. The second row was the components of vector a, and the last row consists of components of vector b. So this was the rule how we calculated a cross product of ordinary vectors. Let's get back to our nabla operator. Nabla is a vector. So you could even come across this notation. But what's the difference? No difference at all. You immediately recognize that this is the cross product, and that is why you're just applying the same rule. I'm just rewriting this rule from here. So the first vector is our nabla vector with these placeholders, and the last row, the third row, consists of components of vector f. That's it. And after that, you can do this multiplication and so on. You have quite a big experience in it. So it turns out that indeed this nabla operator is very convenient. It allows us to write down some formulas in a very concise and clear way. So this is a good news. So hopefully I managed to convince you that this is quite a good thing. And by the way, all these expressions which I wrote down here, they have special names in vector analysis. So for example, the first guy, nabla times phi, scalar factor phi, is called gradient of the function, gradient. gradient of the function. The second guy, which was the scalar product, it's called divergence. Divergence. We are going to discuss these concepts in more detail, of course, later. And finally, this guy is curl of the vector field. So just from the very beginning, so that you know that we are going to deal with these concepts. Okay, so this was introductory part. It was all about how useful and how wonderful this nabla operator is. Okay, let's switch to the next topic. The next topic will be let's just discuss fields. You came across the concept of field watching your lectures, of course, very often. And your lecturer kept saying vector fields, scalar fields, vector fields, scalar fields. So let's discuss this, guys. Fields. So fields can be of two types, as you figure out from your lectures. They can be scalar fields, and they can be vector fields, What do they mean? You know, again, I'm going to divide my page into two columns, because that's where I'm going to discuss everything related to scalar field here and vector field here, so that you can get an idea of the layout of this module, actually. Okay, so let's start. What is scalar field? What does it mean? What is field at all? Let's imagine that it actually means that if you are in 2D space, if you're on a plane, if you're dealing with two components only, it means that you are given some scalar function phi dependent on x and y. But why didn't they just call it scalar function as before? Why do they go to this fancy term, scalar field? You can imagine the situation being like this. So you are on the plane, x and y coordinates. Every point on this plane has two components, two coordinates, x and y. And this relationship means that every point on this plane gets assigned a particular value of scalar value phi. Phi is a scalar, of course, number. That is why you can imagine that there are so many points on the plane, just infinite number of points, and everyone gets assigned number phi, scalar phi associated with it. That is why we can talk about the scalar field. Over the plane, you are given the scalar field. Or on 3D, of course, this every point has three components. That is why the relationship should be written like this. So every point in the 3D space has three components, but nevertheless, every point gets assigned only one value of phi, which is scalar. That is why it's called scalar field. Okay, what about vector fields? It's very easy. In case of vector fields, 2D again, every point on this plane gets assigned not a number, not one scalar, but some vector. So the relationship could be written like this. So vector f gets associated with every point. And in 3D, almost the same, but I'm not lazy to rewrite it. So every point has three components, x, y, and z, and it has some associated vector. Okay, I think it's better to no. What about visualization? Can we just draw a picture of this scalar and vector fields? Let's start with vector field. It's much easier, even though it sounds strange. So let's imagine that we are dealing with 2D case. We are on the plane, x and y coordinates, everything is usual. And every point in this plane gets assigned some individual vector f. So for example, this point has this vector f. This point has this vector f, and so on and so on. So to visualize your vector field, you just need to draw all these vectors to plot them. That's it. So very easy, very straightforward. But you know what? When it comes to scalar fields, things are not as easy, because how can you plot numbers? Indeed. So let's imagine that here's the point, and I want to plot the number phi, which is associated with this point. There's no way to plot the number. Maybe if you only try to plot the surface, but it should be done in 3D coordinate system. That is why mathematicians came up with another method. They use so-called contour plot. Let's write the name here. Very bad marker. I need to throw it away. So it's called contour plot. And it usually looks something like this. Lots of curves here, and they just fill up the whole plane. What does it mean? You know, it actually means maybe this picture, this drawing reminds you of something. Maybe it reminds you of the geographical maps. And you know, indeed, this is the best example when we start understanding the concept of scalar field. You know what? Actually, we are all pretty familiar with geographical maps, and they are especially interesting when they are depicting mountainous areas. So you can immediately realize that, oh, it does look like a mountain. But in geography, they usually they do use these lines. They have somewhat different name. They are not called contour lines or level curves. They have a special geographical name. I don't remember it, to be honest. But what do you usually notice in these maps? Every line in these maps gets assigned some number. So, for example, this is like 2,000 meters above the sea level. This is the height of the point. If you move along this line, this level line, level curve, we mathematicians call it level curve. The height, the altitude above the sea level remains the same, 2,000 all the time. And this level curve means that this altitude will be higher. It's usually like maybe 2,000 and a half. And this is going to be the summit, like 3,000, I don't know, maybe 4,000. Let's make it 4,000. So it does look like geographical map. Why is it considered to be scalar field? Because, you know, every point on the surface of the Earth, of our planet Earth, has two coordinates. They are not quite, of course, Cartesian coordinates in geography. You know, they use longitude and latitude. If I pronounce this word correctly, but it doesn't matter. So in any case, any point on the planet Earth, on the surface of the Earth, has two coordinates. These are x and y in our case. And so every point on this plane, x and y, gets assigned altitude, the elevation above the sea level. So this is phi. This is our phi. So this is a typical scalar field, 2D scalar field. And the role of the function of the scalar places the altitude above the sea level. That's it. Okay, so this is a contour plots, level curves. These curves also called level curves or just contours, level curves. Oh, I'm using the wrong marker. Okay. Okay, so what else? So this is about visualization. And you have plenty of problems, of questions in your tutorial to plot these curves. We are going to start dealing with it quite soon. I need to plug in the charger. What else are we going to discuss today? You know, the thing is that when it comes to scalar fields, not only do you need to learn how to plot these level curves, this is going to be only task number one, concept number one. We also to discuss gradient vector here in this topic. Then the next topic will be directional derivative. What else? I don't remember what else. I want to just make a list here. Somehow I can't remember. Yeah. So maximum change of rate of the function. Maximum change of rate of our function phi. Sorry for my bad handwriting, but I'm going to write down these topics again, of course, these titles. And finally, normal vector to some given surface, to the surface. I'm invading this territory of the right column, but that's okay. So that's what we are going to discuss today in this tutorial. This tutorial, the big part of this tutorial is devoted to scalar fields. And then what about vector fields? What is the layout of the concepts? We are going to discuss two concepts here, divergence of vector field, and the next concept will be the curl of vector field. But this all happens during the next tutorial. So that's it. This is the layout of our, today's tutorial and the next time tutorial. So this is the layout. Okay. So the third topic will be scalar fields. It's time to go into more detail about scalar fields. And so let's start with what? Let's start with level curves. Level curves. So let's organize subtopics here. So subtopic number 1 will be level curves. Level curves. Level curves. What are these guys? Level curves. Level curves, which if you draw all of them, they will form so-called contour plots. Contour plot. Contour plot. So we need the definition actually. What we need the definition. Definition sounds very, very easy, extremely easy. Definition goes like this. So you're given some scalar field. Notice that I'm not using the old words. The old words were scalar function. Scalar function. Now it's better to use scalar field. So we are given scalar field. And what is then level curve? Level curves are given by a very simple formula. You need to set your function of phi, function or scalar field, to some constant and solve this equation. Solve this equation and try to plot it. That's it. So this is the definition of these level curves. And of course, we need example. We need maybe even not one example, even a couple of examples. Let's start doing examples. So the first example will be question 1a. Question 1a from our tutorial sheet. It's slightly out of view, I'm afraid. So in this question, you are given function phi to x minus y. It's equal to x minus y. Very simple function. And you are asked to plot these level curves. Okay, let's start applying this definition. So we need to do what? We need to set phi equal to constant c. Let's denote it c. Then substitute the expression of the function to this. And I think as we are going to plot all these things, it's better to express y in terms of x. Y is equal to x minus c. So this is our main equation, which gives us level curves. But you know, unfortunately, you immediately realize that c is like a parameter here. C can take any value from minus to plus infinity, and that is why it's not one curve which is hiding behind this equation. There is a multitude, a collection of curves here. But of course, we are not required to draw all of them. It's impossible. There is an infinite number of these curves. I think it's a better idea to maybe to plot maybe 4, 5, or 3 of them, just to get the idea of how this scalar field behaves. So let's start. Let's prepare the coordinate system first. So I'm going to plot these curves here, and here I'm going to do some calculations. What sort of calculation? I need to set c equal to some nice constants, for example 0. Let's consider that c is equal to 0. What do we get? We will get that y is equal to x. You immediately recognize it. This is a straight line. This is a straight line. I want to find a nice marker. Which passes through origin. It looks something like this. So it corresponds to phi is equal to 0. Phi and c is equal to each other, and that is why it's a good idea to draw this. It's like in geography, you know. This one of these first level curves. Okay, let's continue. So let's set c is equal to 1. We will get this equation, and again this is a straight line again, but it's a little bit shifted compared to the first one. It's shifted downwards by 1 unit if you look at this y-axis. So it looks something like this. So it corresponds to phi is equal to 1. Okay, good. Okay, let's see be equal to 2 now. So y is equal to 2x minus 2. We have another straight line which gets shifted even further down by 1 more unit. Okay, and then this one corresponds to phi is equal to 2. So you already have the idea that if you increase the value of the function, which is c, your level curves move further and further down. But you know, it's a good idea to consider some negative c. Okay, in this case, we will get y is equal to 2x plus 1. It's again the straight line parallel to these lines, but it gets shifted upwards this time, upwards by 1 unit from here. But I'm not going to write anything. So you get the idea. So now you get the idea of how this scalar field behaves. It does look, maybe it doesn't look like quite like a geometrical map, of course. It doesn't look like mountain, but something, something similar. Okay, very abstract. Okay, let's do one more example because we have plenty of time today. As I said, I'm determined to record all this tutorial, even though it's going to be a very long tutorial. But I think that you don't mind me recording. Okay, question 1D. I really like question 1D. In this question, they have another scalar field. Phi is equal to x squared plus y squared. Let's try and draw contour plot here as well. So according to the definition, we need to set up this guy to constant and try to draw 3, 4, maybe 5 of these contour plots. But you can immediately notice that this C can't take negative values, because if C is negative, like -1, -2, this equation just doesn't make sense, because the left-hand side is positive all the time. And the right-hand side cannot be negative at all. That is why we can use only positive values, including 0, of course. Let's start with 0. If C is equal to 0, x squared plus y squared is equal to 0. There's only one point which satisfies this equation, when both x and y are equal to 0. This is the origin. And that is why our first level curve will look very strange. It's not even curve, it's just one point. It's just one point. And it corresponds to phi is equal to 0. Okay, very strange, but let's move further on. Okay, so the next value of C will be 1, for example. 1. We will get this equation. Of course, you recognize this equation. This is the equation of the circle. Circle with the radius 1. So let 1 be here. 1 be here. And so this is the circle with the radius 1. And let's write that it corresponds to phi is equal to 1. And finally, let's consider one more value of C. For example, 2. X squared plus y squared is equal to 2. This is a circle again, but be careful. The radius is square root of 2. Square root, not 2, but square root of 2, because here this is r squared. So we can put square root of 2 here and draw the circle. Draw the circle, but it corresponds to phi is equal to 2, not square root of 2, but 2. Okay, so I think it's pretty enough. This time it looks more like a geographical map. It looks like maybe very regular mountain. No, it's not a mountain. Look at this, by the way. Phi is equal to 0 here, and when you start moving out of the center, your phi is increases. It's not like a mountain. It's quite an opposite. I think it's I don't know the English word antonym of mountain or hill. What is this? Is it whole crater, maybe valley. Thank you, valley. I was tempted to call it like a crater, valley. So it looks like a valley, but we are going to discuss this concept in more detail now. Okay, so now you have pretty clear idea of how to plot these level curves. Nothing fancy, as you can see. Crater works too. Yeah, thank you. Okay, so now it's time to switch to the next concept, which is gradient vector. What is this guy? Actually, the definition is very, very simple. It's just a formula. Let us consider definition first. So definition is pretty straightforward. So gradient, I prefer to write it with words first. So gradient vector is equal to nabla, our all acquaintance number, times 5, where 5 is scalar function, scalar field. And of course, so it turns out we've been dealing with the gradient already. We just didn't use this word so far. But it turns out this is a gradient. And if you want to expand this expression, we already did it before. That is why I'm not going into too much details. So it will be vector with these components, d phi over dx. The second component is d phi over dy. And finally, d phi over dz. So basically, essentially, gradient vector is just a vector whose components are partial derivatives of our scalar field, scalar function phi. That's it. So that's it. So the definition is very simple, but let's just try to get used to this definition. Let's do a very small example, not even from the tutorial sheet. It's of my own invention. So we are given function phi, which is x squared plus y cubed and plus z to the power of 5. And our task is to find the gradient of this function. You don't need to know what is the gradient about. You need to know only the formula. That's it. So let's start doing. So our nabla phi is equal to, I prefer to rewrite formulas all the time because it's much more convenient. So I'm writing this formula first. And now after that we realize we need to deal with partial derivatives, so-called partial derivatives. Of course, you're supposed to know everything about partial derivatives. And that is why it's not my task to explain them to you from the very beginning. But maybe it's a good idea to refresh your memory a little bit, because I suspect it was long ago when you last studied partial derivatives. So what are partial derivatives? So you can see the function, it's dependent on three variables, x, y, and z. But when you want to find the derivative related to x, in relation to x, you should imagine that all the other variables, y and z in our case, gets frozen. They turn into constants. And that is why when you start differentiating this expression, you should perceive them as constant. And that is why, for example, let's look at the second term. The second term is constant. The third term is constant as well. And that is why derivative for the constant is 0. That is why you write down the derivative on the first term only, which is 2x. And these two guys are 0. I'm just writing it into detail. 2x plus 0 plus 0. Now, when we start dealing with this derivative over dy, you need to freeze this x and z, which means in our case that the first term and the last term becomes constants now. So it looks like 0 plus derivative of y cubed, which is 3y squared plus 0. Okay, and finally, we are dealing with the derivative over dz. In this case, only the last term will be still alive, if I may say so. And the first two terms are frozen. So 0 plus 0 plus 5 times z to the power of 4. Of course, it's better to simplify this. It looks too messy. And this is the end to our problem. So finally, we can rewrite it as 2x, the first component. Oh, sorry, sliding away. 3y squared, the second one, and the last component is this one. So that's it. So technically, it's just a piece of cake to calculate the gradient vector. You just need to remember this formula. It's the first operation which we discussed before in our introduction. So it's just like a multiplying nabla vector by scalar, by some constant. Okay, but what about the understanding of the meaning of this vector? Sorry, I need to prepare my screen again. Because maybe if you've gone through this tutorial, if you went through this tutorial before this tutorial, you probably noticed that there are so many questions in this tutorial related to gradient. Sometimes you ask to plot this gradient. Sometimes you need to use them. There are actually many questions here. And to be able to solve these problems, you should know properties of a gradient vector. Let's write it down. Properties of gradient vector. I'm sort of lazy to write the word gradient anymore. So nabla phi, just nabla phi, it means gradient. Okay. So what are the properties? The first property, the most important one, is the reason why this gradient was invented at all. It turns out that gradient, nabla phi, shows. It's so important that I'm not even lazy to write it down in words. Shows the direction. It shows the direction in which our function phi, our scalar field, increases the most rapidly. So let's discuss this geographical map, my favorite image actually. So let's imagine that we have the image of the mountain, and it looks like this. So this is our image of the mountain. This was 2,000 meters, this was 2,000 meters and 500 meters and so on. This is summit. So 2,000, 2,000 and a half and so on. Okay, so what about gradient? So let's imagine that we are standing somewhere here at the foot of the mountain, for example. We are standing here, and in which direction, and our function, our scalar field is altitude, is the elevation above the sea level. So this is our phi. And we are going to decide in which direction we should move to get the elevation gain most rapidly. Of course, the answer is pretty obvious. You should head right to the summit. So this is the direction of your gradient. So gradient should point the way where you get the elevation gain most rapidly. Of course, it's better to head right to the summit. But you know, it's quite a rough explanation, but we are going to discuss more properties now. Wait a little. Okay, so we can get back to, no. Let's discuss the second property first, and then we will be able to plot some curves, actually. Okay, the second property is that, but you know, my picture here is very bad, actually, very careless. The second property is that your gradient, which is nabla phi, should be orthogonal to the contour level curve. What does it mean? Let's make another picture, much better one. So let's imagine that let's draw one of these level curves, only one of them. And you are interested in this point B. And you are interested, you know that the summit is somewhere here. Okay, so you want to plot the gradient. You know that it points this way because the summit is somewhere here. But at the same time, you need to try and plot it approximately perpendicular to this level curve. So it shows like this. And if you want, if you're interested in this point, you should be careful to plot it not only in the direction of the maximum increase, but also to be orthogonal to this curve and so on. And so maybe for this point, the gradient will point here and so on. Very bad handwriting, by the way. So this is the trick, not a trick, this is a property of the gradient vector, and then that gives you the tool how to plot the gradients properly. Okay, but you know, before diving into examples, I need to discuss the third property because it's a good idea to have them all in one place. What is the third property? It turns out that look at this picture. Even though it's quite a careless picture, but nevertheless it's quite good. Look at this. Let's imagine. Of course, you can imagine. You can immediately figure out, looking at these geographical level curves, that this slope is quite a gentle slope of the mountain, and this is quite a steep slope. And so gradient, actually, we want the gradient to reflect this fact that this is the you know, gentle ascent. If you start going to the summit in this direction by this slope, and this is very rapid ascent, and so it's reflected by the magnitude, by the length of this vector. So let's write down this fact. So the steeper the hill is, the climb. So the climb is, the longer the magnitude, or the longer the magnitude of gradient vector is. So the magnitude of the gradient vector is inversely proportional to the steepness of your climb. This is a third consideration which could be useful for plotting, our future plotting. And let's try and apply this third property to this drawing. Even though it's quite a careless drawing, but nevertheless, it's quite good to illustrate this idea. Let's imagine two extremes. So one person stands at this point, in this green point, and another person stands in this blue point. So, and they both want to go to the summit. For the first person, it will be quite, you know, gentle ascent. And that is why the gradient vector should be quite short. So the change of rate for the elevation for phi will be quite slow, and that is why the vector should be quite short. But for this person, the extent will be quite rapid, because in this case gradient should be much longer than this one, So the relative magnitude of the gradients does matter, in some problems. Okay, so this was introduction to the concept of a gradient, and now it's time to start solving our questions from our tutorial sheet. By the way, the first one, I think it's a good question number 8. Question number 8, which is actually has a picture. You have a picture. Oh, you even have 6 pictures in this question. I lost my tutorial sheet. I don't know. I almost recovered it. Yeah. So your question 8 looks like this. You have 6 pictures here with 6 fields, scalar fields. It's already it's already the answer. Sorry, I'm showing the wrong picture. So this is the picture. So this is question number 8, and you have 6 plots here. 1, 2, 3, 4, 5, 6, and in each case you are asked to plot the gradient vector. Okay, but I'm not going to do all of them. I'm going to do only this one. So let's rewrite. Let's copy this picture here. So they have like 4 level curves here. This, something like this, roughly. And they have the values of our scalar function. Is the first curve corresponds to minus 0.8. This one is this value, and this value. So you're pretty familiar with these pictures. So these are all values of our function phi. We don't know the physical nature, the geometrical nature of this phi. We don't care. All we need to do, we need to plot our gradient vector. Immediately you can see that if you move this way, from here, from left to the right, you will get the increase of the phi. That's why our gradients should point this way, and this way, not this way, of course. And the second consideration is that they should be plotted roughly perpendicular, roughly orthogonal to these curves. So, taking all this into consideration, the first gradient will be like this, the second like this, third like this. So we can plot many gradients for this particular curve. You should plot some gradients for the second curve as well, from here. So all the gradient vectors should start on the particular curve, and here as well. And I think that magnitude of this, and so on. And so you immediately get this vector field, by the way. Yeah, gradient. If you look at all the gradients, like the whole collection, you will realize that we are plotting a vector field now, but it doesn't matter. It's just a side mark. Okay, and as for magnitudes of the vector, you can see that the slope is equal all the time. The distance between the curves is equal. That is why these vectors should be equal as well. So this is the first question which we answered in connection with plotting these gradients. But now it's time to get back to our question 1, because actually I haven't finished this question 1. Because apart from what did we do in question 1? We plotted the curves, but we didn't plot gradients. They also asked us to show the gradients, and that's what I didn't do actually, because we hadn't discussed gradients by then. So let's do it right now. So let's get back to question 1a. Question A, we had a function phi which was equal to 2x minus y, and of course I'm not going to do it all over again. I'm just going to copy the resulting plot from the previous page. So we had a collection of straight lines there. Do you remember this? Of course. So, and this was corresponding to phi equal to 0. This was 1. This was 2, and so on and so on. So I'm just copying this contour plot from the previous pages. Okay, and now, because now we need to plot gradients, to show gradients here. But you already have some experience. So of course you need to head to go in this direction to get the increase in number 5. And at the same time you should try to remain orthogonal. So this is our first gradient, second gradient, and so on. There are there are multitude of gradients corresponding to this particular level curve. The same for this curve. Try to plot them with the same magnitude, actually. And this here and here as well, and I'm getting lazy already. So you get the idea. So we finished task question 1A now. And also we had question 1B with the circles. Do you remember? Let's get back to it. We have plenty of time today because I'm going to record everything. So question 1D, it was question 1D. In question 1D, our contoplot looked like collection of circles. Let me remind you. So this was our first circle, this was the second circle. We even had the point in the origin. So this was 0, this was 1, this was 2, and so on and so on. And of course, you realize that it looks like a crater. Yeah, it looks like a crater with the bottom here, because the phi is the minimum, lowest, the smallest here. So it's like a center of the crater, and these are like slopes. And so gradients should point, to this direction, here, 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 and here. So these are going to be our gradients. These are gradients for 5 is equal to 0. If you switch to the next level curve, 1, the gradients will be pointing this way and try to remain orthogonal to this circle, and so on, and so on, and so on. And I don't know about magnitudes, actually. Maybe magnitudes are not quite equal, but it's quite difficult to realize it. To know everything about magnitudes, it's better to calculate, actually, to draw more level curves. Now it's not quite clear whether we should take care of magnitudes or not. Because the previous example was pretty straightforward. We did realize that the distance between these straight lines is quite equal. That is why our gradients had equal magnitude, equal length. But as for this picture, we were sort of lazy to draw all this, to draw many of these circles. And that is why I had no clear idea whether the distance is equal between the neighboring level curves or not. That is why I don't care about it too much. So now I suggest we do one more question 1, because it looks really interesting. I really like it. From the very beginning. So question 1B, it's going to be question 1B. Oh, sorry. Just question 1B. Let's do another one. Question 1B. Here you have function, given function phi is equal to xy minus y. And the assignment in this question 1 was actually contoplot, to do contoplot, and also show gradients. Show gradient vector, gradient. So let's do everything from the very beginning. Let's spend like maybe 5 minutes on it. Okay, so let's start doing. So we should set phi is equal to c, which is equivalent to x squared minus y is equal to c. And then we can express y from here. Y is equal to x squared minus c. And of course, you immediately realize that this is going to be a collection of parabolas. Let's draw a couple of them, or maybe 3 or 4. Okay, if we set c is equal to 0, we will get y is equal to x squared. This is a parabola passing for the origin. Parabola passing for the origin. You know what? I need a bigger picture. No. I'm going to prepare all this, level curves, but then I'm going to make a bigger picture. So let's just prepare. So when c is equal to 1, we have this parabola. When c is equal to 2, we have this parabola, and that's it, I think. 3 is enough. And now I'm going to use actually quite a big picture, because I want to be very careful with my image. Very important. So this is our coordinate system, and for c is equal to 0, we had parabola y is equal to x squared. This parabola passes through the origin. Very familiar parabola. So this corresponds to 0. Phi is equal to 0. The next parabola corresponded to c is equal to 1, and it was shifted downwards by 1 unit if you look at the y-axis. So it was looking like this. The second will look like this. And try to make them as long as possible. The third parabola was corresponded to c is equal to 2, and it was shifted by 1 more unit down, and so on, and so on, and so on. And of course, we immediately set the tangent. So this was corresponding to 0, this to 1, this to 2. And finally, you already got the tendency. You can easily draw more parabolas if you like. No problem at all. This corresponds to 3 and so on and so on. It's time to stop. Okay, and so we've done the first task. We did plot the contour plot. What about next? The next task is to show gradients for each curve. And you know, of course, we already have some experience. We know that gradients should point this way, this way, this way, and try to plot them roughly orthogonal to our curve. I'm plotting gradients only for the first curve because I don't want this plot to be very messy. But what about magnitudes this time? I think that magnitude, as you remember, reflects the steepness of your climb, the steepness of the slope which you are climbing. And look at this. It's pretty obvious for this picture that this looks like a mountain again, parabolic mountain, very, very abstract mountain. But nevertheless, you can even easily see that this slope looks much gentler than, for example, this slope, of course, because these level curves are more dense. They are closer to each other here in these areas. The farther you go from the origin, the denser this picture becomes. And that is why the gradient should be longer here. So there is a tendency. This slope, it looks like this area is the gentlest one. That is why the gradient should be the shortest one here. And once you shift away from the origin, this gradient should be a little bit longer. This will be longer, longer, and longer. So maybe I'm exaggerating things a bit, but I just want you to see the tendency. So the denser, the closer to each other these level curves are, the longer the gradient is. So that's how you should plot gradients, and of course orthogonality. So I'm not going to plot other gradients corresponding to other curves because it will make my picture too messy. So you just need to get the idea. Okay, but we are not finished with gradient plots yet, because you have one more task in this tutorial sheet, which is a reverse task. So what was our task so far? We were given a contour plot and we were asked to show gradients after that. But the reverse task is just the reverse one. You are given gradients and you are asked to plot these level curves. Okay, so question 9 is a reverse problem, reverse task. Reverse task. Very fancy. This is question 9. You know, it's actually, I can show it to you. So it looks very fancy, but you know what? I'm not going to solve this particular task. It's better to leave it for your homework. I'm just going to give you multiple small examples so that you can get idea how to do it. Maybe you already have some considerations, some ideas. Okay, let's consider several very small, very simple small cases. Let's imagine that our gradients, we can even plot is this in the coordinate system. So this is coordinate system, x and y. And let's imagine that you have a collection of gradients. So these gradients are all parallel to each other, and they all have the same magnitude, roughly the same magnitude. I'm not a good artist, you know, but nevertheless, I'm just saying it to you. So this is how our gradients look like. How on earth can we plot these level curves? You know, we know the property. The level curves should be perpendicular to our gradient vectors. And this, so if you start at this point, for example, you can move downwards or upwards, but trying to remain perpendicular to these vectors. So it turns out it's very easy. It's another straight line, and here as well, and here as well, and here as well. Very easy. And you know, what about the density of these curves? You know, as our vectors all have the same magnitude, that is why the distance between the level curves should be roughly the same. So this is the very first example. This is the first example which has been completed. So that's how you should plot these level curves. You should start at any point on the plane and start moving, trying to remain orthogonal to your vectors, and that's it. And after that, after you plotted several curves, like 3, 4, 5, and then maybe. After that, you need to start worrying about the density of these curves. This time, you look at the magnitudes of this vector. Okay, let's do more examples. Let's do pretty similar example with these parallel gradients. So this is going to be second example. Again, this is our coordinate system. It's not necessary actually to plot the coordinate system actually, but this is my just habit. Okay, this time you are dealing with this parallel vectors, but there is a tendency. Look at this obvious tendency. If you go to the right, move to the right, these gradient vectors become longer and longer. What does it mean? So they become longer and longer. So you see the tendency. How do we need to plot level curves? At first, you don't need to worry about the length of this vector. Just worry about being orthogonal. So start at any point somewhere here and try to move remaining orthogonal. Again, we are getting these straight lines again, vertical lines. They're not quite vertical. And after that, so it looks pretty the same as the previous example, but this time we need to take into consideration these magnitudes. There is a tendency. If you move to the right, the gradients become longer and longer. It means that you need to plot more curves here to show this tendency to become closer and closer to each other. My drawing is not very good, of course, but you know the tendency. So it looks like the slope is becoming steeper and steeper in terms of geography. Okay, finally, maybe one more example with some more complicated gradient field. Okay, let's imagine that we were dealing with the circle this time. So you have gradients which look like this, maybe. So here, here, here. So they are moving in this way, these gradients. And this and this and they all have the same magnitude. They all have the same magnitude. So what do we need to do? The same thing. We choose the random point on the surface, so here, and try to move remaining perpendicular to this point. Of course, you will end up drawing circles. At this point, if you start at this point, you will end up having circles, and so on, and point here, of course. And so that's how this contrast looks in this case. And as the magnitudes of the vectors are the same, so the distance between these neighboring curves is approximately the same. So this is the idea how to do this reverse task. And I think that you will have no difficulty to solving this question number 9. I leave it for your homework. Okay, so so it's been 50 minutes, and the end of this tutorial is not very close here. Okay, the next concept. So you are welcome to leave this tutorial without saying goodbye to me, because I know that I'm pretty aware of the fact that you are having the next tutorial. But if you are free, you can stay, because I suspect that I'm going to talk for another hour. Okay, so the next concept will be directional derivative. Let me use this one. I don't know, concept number 3 probably. Yeah, number 3, directional derivative. Directional derivative. What is this guy about, first of all? Let's write down the definition and get used to it, and only after that we can discuss this concept. So you're given scalar field as usual, phi is dependent on the coordinates of the point. Okay, and this time you're also given direction, which is given by some vector y. These components again, directional vector y. How can you calculate? No, it's better to discuss the meaning of this concept. You know what? The idea is very simple. Let's imagine our favorite example about the mountain. Where is it? So this is our favorite example about the mountain. Do you remember this? So let's imagine that we are standing somewhere here at the foot of the mountain, and in which direction can we start moving? The answer is that there are a multitude of directions. So you can start moving this direction, this, and this. Oh, there is an infinite number of directions actually. But what is the problem? What is the problem with these directions? The problem is that you are interested in having the elevation increase because you want to head to the summit, or you're just interested in how rapidly my altitude above the sea level will increase if I start moving in this particular direction. And of course, looking at this picture, you realize, and you from life experience, you realize that it all depends on the direction. If you start heading towards the summit, this will be the most rapid elevation gap. But if you start moving in this direction, like zigzagging, sometimes people do have to move in zigzags in the mountains, the elevation gain will be slower, and slower and slower and slower, and sometimes you even end up having elevation decrease, of course. So this directional derivative shows you this change of rate of your phi when you move in a certain direction. That's it. And the maximum value of this direction derivative will be, of course, in direction of a gradient, but we will discuss it later again. So the meaning of this directional derivative is pretty clear now. What is the formula? What is the definition? Definition is as follows. So d phi over du, this is a notation, and I think it's pretty nice notation. Derivative over along this direction. So it's our gradient, nabla phi, times scalar product of a unit vector of direction. So this is our formula. This is just a formula. So it's just a piece of cake, actually, to calculate your direction derivative. You just need to remember this formula to understand this. Okay, but let's do some clarifications here. So this is, I prefer to use orange. So this is our gradient vector. Let me remind you, gradient vector. And this is the unit vector of our direction. U hat is usually used for unit vectors. And looking at this formula, you immediately realize what you need to do to calculate this derivative. You need to calculate the gradient. We've done this task several times today. And you also need to normalize this directional vector, which is always given to you. The only thing which I need to point out to you that usually they also give you the point. We are interested in the directional derivative at this particular point P. And this means that we can add P here. And this means that you, after calculating the gradient, you need to substitute the coordinates of this point P into this formula, given formula. And after this, you can perform this scalar product. That's it. Very easy, very easy. But nevertheless, I'm going to go over some example. Okay, this is going to be question 2a from our tutorial. Question 2a. So in this question, you are given function. Look at this. Notation is different, which is actually very good. They haven't notated it like phi as usual, like f. I think it's a good idea because otherwise you might get too used to one notation. Okay, so you're given function. You are given a scalar field, sorry, a 2D scalar field, and you're also given a point pi with coordinates 3, 1, and also you're given direction u with coordinates 1, 1. And you are asked to find the derivative of our f along this direction. So what do we need to do? We need to look at this formula and realize that we need to do it by step. We need to find the gradient, our function first, then substitute the coordinates over p. This is going to be our first term. Then we need to normalize our direction vector, and then after that we can do dot product or scalar product of them. So it's pretty clear, very straightforward, nothing fancy. You don't need to understand you don't even need to understand the meaning of this directional derivative. Okay, let's start. So nabla f first. This is nabla is our gradient vector. This time it has two components, of course, df over dx and df over dy. So it's pretty easy to do it. So the first derivative over x is 4x minus y, and the second component will be minus x. I'm not discussing how I calculated these partial derivatives because I'm assuming that you're already pretty familiar with this from your last course, previous course. Okay, now we need to calculate it in our point P. That means that we need to substitute the coordinates of point P. Let me rewrite them here. Okay, let's substitute. So 4 times 3 minus 1, and this will be minus 3. So finally we get 11, the first component, and minus 3, the second component. Okay, pretty easy so far. Now we need to normalize our directional vector. So the length of the vector is equal to 1 squared plus 1 squared and square root of it, square root of 2. And it means that our u hat, which is unit vector, is vector should be divided by its length. And it will give us components 1 over square root of 2 and the same second component. So we prepared everything, but I've run out of paper as a result. I need to change the page. Everything looks bad now. And finally, we can calculate our derivative. So df over dy in point P is equal to what? Is equal to, let me write down this formula again. So the gradient of this vector in point P times u hat. And let's substitute our results. The first vector we calculated, it was 11 minus 3, and the second vector was 1 over square root of 2 or 1 over square root of 2. And now we need to perform this scalar product, which means the first component times the first component here, which is 11 divided by square root of 2, and minus 3 over square root of 2. It will be 8 divided by square root of 2, and we can even simplify it. 4 times square root of 2. That's it. So as you can see, very, very easy task. There's nothing easier than to calculate gradients, to calculate this directional derivative if you know the formula. But if you need to answer some more sophisticated questions, it's especially about plots, the things might come much more difficult. Okay, so that's it about directional derivative. The next topic number 4, subtopic number 4, will be maximum change of rate. Maximum, number 4, maximum. I forgot to mention these words. So directional derivative actually shows the change of rate of the function when you move in this direction. Okay, so it shows. It's a pity that I didn't mention it before. I didn't even use this word. So maybe it's better to just emphasize this verbally. So the direction derivative shows us the rate of change of our function, of our scalar field, when you move in this particular direction, as well as ordinary derivative for ordinary functions back at school, shows the change of rate in this function when you move along x-axis. This is like a generalization. Okay, so maximum change of rate for our scalar field phi, of course, phi change of rate. What is the maximum change of rate? You know, it's very easy. So because you know the meaning of the gradient, you know the idea behind the gradient. A gradient shows the direction in which our phi increases the most rapidly. And that is why you get this maximum directional derivative in this particular direction. So you should move in the direction of gradient to get this derivative maximum value. In other words, the proof was given in the lectures. I'm just writing this down to you as a result. Maximum change of rate is equal to the length of the gradient. That's it. I think it's easier to memorize this fact once for all. So if you ask to find the maximum change of rate of your function phi, you need just to calculate the gradient and take the modulus, take the absolute value of this gradient. That's it. Very easy. Okay, I should emphasize it to you. So if you understood everything which I explained to you before, so you can say that, oh, it's quite natural. It's pretty obvious. You even didn't need to emphasize this fact to us. Okay, so let's get back to some question. Question 2a, actually. Question 2a. We haven't finished question 2a, by the way. Question 2a. Question 2a, we just did it. The first assignment was to find the directional derivative of this in this given direction, which we already calculated. It was 4 times square root of 2. But the second question was to find the maximum change of rate. So maximum change of rate, I prefer to use it to write these words. It's just absolute value, the length of our vector phi, and what was our gradient. I don't remember it. The gradient in this point, it was 11 minus 3. 11 minus 3. And so to calculate the length of the vector, we have a very easy formula. 11 squared plus minus 3 squared, which will give us square root of 121 plus 9, square root of 130. That's it. So maximum change of rate is very easy. Just calculate the gradients and calculate its length, the length of this vector. That's it. But you know what? Unfortunately, I have to spend some more time over question 5. Question 5 is quite related to this topic. Actually, in question 5, we have a lot of sub-questions, and everywhere you are asked to find this maximum change of rate. But some of the functions, if you look at them, look very difficult. These are so-called complex functions, and that is why I think it's better to discuss one of them so that you don't get lost. So let's go through over example question 5f, at least question 5f. So in this question you have a very strange function. Phi is equal to r squared, where they mention it later that r squared is equal to x squared plus y squared plus z squared. So this assignment looks very strange. The given information looks very strange. And they ask you find maximum change of rate again. Change of rate. You immediately figure out that I just need to calculate gradient of this vector, which is quite easy, which is usually quite easy. But in our task, it looks so strange, actually. But there are several techniques as to how to deal with this problem, how to find partial derivatives of these complex functions, because this relationship looks quite, complicated. So phi is dependent on one variable r at first, but then it turns out that r is dependent on 3 variables. So eventually, phi is dependent on 3 variables, of course. So it's a typical multivariable function. But how to deal with it? There are actually several techniques how to deal with these partial derivatives. But I suggest you should use the most primitive one, the easiest one. You can just substitute this expression into this expression, and that's it. I think this is the easiest way. Maybe sometimes it's not very convenient, but at least it's pretty forward. So what can we do? We should express. Sorry, it was r cubed. It was r cubed. I just noticed this mistake. So all we need to do, we need to express solve this expression for r first, which is quite easy. It will be square root of this plus z square. And after that, we can substitute it our phi. R cubed will be x squared plus y squared plus z squared. It will be square root of this, and then cubed. We can rewrite it. We can simplify it a little bit, probably. It will look better if we rewrite it in this way, in the power of 3 over 2. So this is our final vector phi. So this is one of the ways how to tackle with this situation. I think this is the simplest way, actually. And if you're able to find derivatives, using the chain rule, by the way, you are supposed to apply chain rule here for finding derivatives, then you'll be okay with this method. So let's start doing it. So gradient is a vector whose components are partial derivatives of this function. So let's calculate these partial derivatives. So d phi over dx is what? We need to take the derivative of external function, which is 3 over 2 x squared, this guy in the parentheses, in the power of 1 over 2, because 3 over 2 minus 1 will be 1 over 2. And then we should multiply, according to chain rule, we should multiply by the derivative of internal function, which will be 2x. And the result will be, we can simplify this result a little bit, because 2 and 2, these two guys are cancelled out. So it will be 3x and times square root of this one. Square root looks much nicer. So we have done, we are finished with the first derivative. The second partial derivative, the nice idea is that this function is symmetrical. That is why you don't need to go into the all this trouble again. You immediately realize that should be y here, and the rest of the expression is the same. Okay, and finally the third derivative could be easily rewritten substituting z instead of substituting z with I, or vice versa. I said something. Okay, so these are partial derivatives. Now, did they give us some point or not? Maybe not. I don't know. I should look at this assignment. I don't remember actually. Yeah. We were given some point. We were given point P with coordinates 2, 1, 1, if I'm not mistaken. I can't see properly in this dim light. Okay, it doesn't matter so much. It means that we need to calculate these derivatives in this particular point. I don't know how to do it. Okay, df or dx in the point P. We should look at the different pace. So x is 2 and the remaining variables are 1s. Okay, it's pretty easy. This will be 6 and this will be a square root of 4, 2. 6 by 2, 12, if I'm not mistaken. I hope I'm not mistaken. Okay, df over dy. Let's look at it. So y is 1. This means 3 and square root of 2. 3 by 2 will be 6. And the last derivative, df over dz. Look, let's look here. This is 1. This is the same as the previous derivative, so it's 6. So finally, we have our gradient. So our gradient, nabla phi, let me remind you formula again, just in case, df over dx, d phi over dy, d phi over dz in our point P, of course. And we already have these numbers. This is 12, 6, 6. That's it. And now maximum change of rate is equal to the length of this vector, nabla f, and which is square root of this expression, 12 squared plus 6 squared plus 6 squared. I'm too lazy to calculate it. Okay. I have no doubt that you will have no difficulty to calculate this thing, but I feel a little bit lazy. Okay. So it's pretty clear now. Of course, you can use more fancier technique to deal with this, chain rule. But unfortunately, I don't have time for this tutorial. This tutorial is getting very long anyway, as I said before. If you're really interested in this technique, you can always refer to your previous course in mathematics and revise all these techniques. I suggest you should use the easiest one. Okay, what else? Yeah. Okay, the fifth topics inside these scalar fields, the last one finally, is how to write normal vector to the given surface. Normal vector to the surface, to some surface. It's just a formula. It turns out that this vector is our favorite gradient, actually. That is why it's good to mention this topic inside this scalar field topic. Okay, so you're given surface S, which is usually expressed by this equation, f of x, y, z is equal to some constant. That's how the equations of surfaces usually look like. They look like scalar fields, by the way. Okay, scalar field is equal to some constant. And you are interested in the normal vector. It turns out that normal vector coincides with the gradient to this function. So normal vector actually is nabla of f. That's it. Let's rewrite it. df over dx, df over dy, and df over dz. That's it. And so this is just all you need to know. You need to know this formula, this fact, that normal vector is actually a gradient vector, and that's it. And that is why, you know, my initial intention was to go over question 4, but I think that you can easily do it yourself, you know, using this formula. Nothing fancy about this problem. I think that you are going to cope with this problem. I'm just getting tired a little bit of talking too much. That is why I decided to save a little bit of my time and effort on this task, because it's so simple, this question 4. Because the reason is why I'm saving my time and effort, because the next topic will be really serious. We need to discuss it in more detail. So I'm saving my strength for the next topic. So we are finished with scalar fields, by the way. We are finished with scalar fields. Now you know everything related to scalar fields. Not everything yet, but the basics, because we are going to get back to scalar fields during our next tutorial. It will be, it will be about the connection between some scalar fields and some gradients. So actually, you do know everything about scalar fields. And now it's time to start discussing vector fields. So let me remind you, vector fields means that every point in 2D or 3D space gets associated vector with it. This vector, I don't know, I'm just trying to look for some example from real life. Maybe it's like a river. You can imagine that a vector field is like a river, and every point, every particle in the water, in the moving water, gets associated with the velocity vector. So maybe this is the best example of vector field. I can't come with another example. Okay, it doesn't matter. It's it's that's what your lecturer did actually. I think he gave you a lot of examples. Okay, what is the first concept associated with vector fields? The first concept, as I mentioned earlier, is so-called divergence. So definition. Let's write down the definition first. What is this guy divergence? So let's emphasize the fact that this time you are given vector field F, which has, let's denote the coordinates of the vector PQR. Actually, PQR are functions. Let me write it in a more concise way for next tutorial. No, the thing is that, yeah, it's mostly for the next tutorial, but in this tutorial, they include the concept of divergence, unfortunately. That is why this tutorial is so long. They include question number 10 and question number 7, which are all about divergence, unfortunately. That is why we need to do it. Yeah. So let's imagine that we are given a vector field this time. So every point in the 3D space, in this particular case, gets associated with some vector, with velocity vector, for example. But I denoted the components of this vector like p, q, I, but these are not numbers, they are functions. Remember, that is why I'm going to explain to you. So pi is not pi, it's a function of x, y, z. Q, the same, it's actually the function, and r is the function as well. So actually it's quite a long notation. That is why I'm not going to notate it like this. I prefer to try it in a shorter way. So p, q, r are actually functions. And what are x, y, z? X, y, z are the components of this point in which we consider this vector. Okay, what is divergence? The definition is very, very simple. Divergence f is given by this expression, nabla, our vector number, times vector f. So this is a scalar product. So definition is extremely easy. And of course, it would be interesting to expand this expression. Oh, let's just practice this once again. So our nabla is a symbolic vector with placeholders. Let's rewrite it here. And our vector f has components p, q, r. And this is the scalar product. This is why we need to multiply the first coordinate by the first coordinate, dp over dx, plus the same for the second coordinates, and plus the same for the third coordinates. As you can see, it's quite a nice expression, but maybe it's easier to memorize it using nabla operator. At least when you need to write long formulas, it's much better to use this notation than this one. But they are actually the same. Okay, and the first question will be very, very easy. Question 7 is very easy. It doesn't require you to understand this concept very deeply. It just requires you to know this formula. So In this question 7, you are given vector field this time, which consists of 3 components. The first component is x plus 3y. The second is y minus 2x. And the third one is x plus alpha z. As you can see, there is an alpha here. It's actually parameter. It's a parameter alpha. Parameter alpha, and you need to find it. Parameter finder, but I'm not finished with the assignment. And also you are given the fact that divergence of this field is equal to 0. And the assignment is find alpha, find this parameter alpha. So this is how this task looks like. And all you need to do to solve this question, you need to know the definition of divergence. You need to know this formula actually. So you need to apply this formula, set it equal to 0, and you will get some equation from which you will be able, hopefully you will be able to find this alpha. That's it, very easy task. It doesn't require any understanding. Okay, let's write down our divergence. So divergence is equal to 0. It means that this expression dp over dx plus this partial derivative plus this one is equal to 0. So now we need to substitute our partial derivatives. So this is pi, if you remember. Oh, this is p, this is p, this is q, and the last component is r. This was my notation. So dp over over dx. What is this? It's 1. It's 1. The next derivative over relative to y will be 1 again. And the last derivative will be alpha, just alpha. And it's very easy. Alpha is equal to minus 2 from here. So the task has been done. Very easy task. It was very easy because it doesn't require any understanding. But now it's time to discuss question 10, which is not easy at all because it does require understanding of this concept. So what does divergence show to you? Divergence, judging by the name, it shows the divergence of the vector field, but it's still quite clear. It sounds very, it doesn't sound very clear to you. So you can imagine that divergence can be positive. Divergence can be positive. Divergence can be negative, and it can also be equal to 0. And this is very important. So if divergence is positive, it means that if you imagine that vector field is like fluid moving somewhere with some velocity, so it means that there is a source, you know, like a spring, in this maybe a river, where the water is coming from. So if you have the divergence, it means that water flows out of this source. So this is source. This is called source. This is quite an opposite situation. So your vectors just are being created out of nothing, out of this source. Okay, divergence, when it's negative, it means quite the opposite situation. I wonder, what is the opposite word to the source? Is it sink or drain? Which is better? Maybe drain, I don't know, I'm not sure. Maybe you can help me. Sink, sink, really, sink, I'm not sure, sink, okay, let it be sink. It means that your particles of water, they just disappear somewhere. Like you can imagine there is a river, not river, canal, maybe canal. There can be sink in canal, so water disappears there. And if divergence is 0, it means that everything goes smoothly. No water disappears, no water, are being born out of nothing, and that's all. So it's quite, abstract concept anyway. But moreover, you need to apply this concept, your understanding, to some, concrete tasks. Okay, let's start. So it's connected with question 10. It's question 10, this task. So what is this question about? You are given a very scary picture, to be honest. You are given the vector field looking like this. I'm not going to solve this particular problem. I'm just give you the idea. There are lots of vectors here. It's a typical vector field. They have a different direction. They have different magnitude. And your task is to determine where divergence is positive, where negative, and where it is equal to 0. It seems to be quite impossible now. And I have to admit, this task is much more difficult than the previous one connected with gradients. Let's start with a very small task. What technique should you use to So your technique can be compared with the gold digging, for example. So imagine yourself, there are gold diggers who use these metal detectors, to discover gold, of course. But you can imagine that your task is pretty similar. You are not a gold digger. You're not looking for the gold. You're looking for sources and sinks in your river, for example, or in your canal. And you are allowed to use special device which looks a little bit like this metal detector. So this is the only way you can discover these sinks and sources. You're moving along this river, along this canal, using this metal detector or source detector, whatever it's called, and that's how you can find these sources and sinks. There's no other way to do it. You just can't do it just looking at this vector field, because it's very confusing. Okay, let's start with very, very simple example. This is actually the highlight of this tutorial, because this is the most difficult task. Okay, let's start with a very, very simple example. Let's imagine that our vector field has parallel vectors to each other, and they all have the same magnitude. We already used this field when we were discussing a gradient, but this task will be quite different. So it's like a water flowing in the canal. And of course, by intuition, you immediately realize that there can't be any sources or sinks in this river, because every velocity is equal to each other. But we need to prepare for some more sophisticated task, like the one depicted in this tutorial sheet. That is why let's start thinking in a more general way. What technique should you use? What is the equivalent of this metal detector in your case? So remember that, imagine that you are traveling along this river, around this canal, holding this detector in your hands, like a metal detector. How it should look like? It should look like a rectangle, like a box. So you draw a box. Two sides of this box should be parallel, and they should be orthogonal. No, two opposite sides of this box should be parallel to our vector lines. So this one and this one. So these are two sides of this future box. They're parallel to our vector fields. And the other two sides of this box should be orthogonal to these lines. So let it be this color, and this will be orange. Where's my orange? Orange is here. So this looks like your metal detector, this box. So you're holding this box in your hands, and of course, and also try to imagine that you are moving in 3D space. So this vector field looks like a 2D field, but in reality, it has a height above this piece of paper. And that is why your box actually has, these are walls of the box. This lilac and this orange, these are walls of the box. They are not straight lines, they are walls. You're just looking at the box from above. Okay, so we use this box to detect our sources, probable sources or sinks. Let's call this, as you can see, the vectors go inside this box, the fluid goes inside. This is why it will be in the front face of this box, and this will go out, and these vectors go out of this. This will be the the back front, or maybe in and out. What are you interested in? You are interested in so-called flux of water into this box. Flux. You're pretty familiar with this term. What is flux? Flux is actually defined over the surface. Of course, this front face of the box, it's like a surface. It's like, you can imagine this surface, and it has the area. So the flux is the product of all the vectors coming into this surface, into this lilac surface, times area of this surface. So this is the flux. And it turns out that divergence actually is the flux out minus flux in. And it's approximately flux out minus flux in divided by delta, but it doesn't matter now for our test. So you should compare the flux out and flux in. And if flux out is bigger than flux in, it means divergence is what? Divergence is positive. Okay, let's write down this fact. If flux out is bigger than flux in, flux in, which goes into this box. It means what? It means that water, the amount of water entering this box is smaller than the amount of water leaving this box. It means that it definitely, the water is being created somewhere inside this box. It means that there are sources inside this box. And sources means that divergence is positive. Divergence of this field, I don't know, F, is positive. That's how you can test this this field for the presence of sources or sinks. And the opposite situation, if the amount of water entering this box is bigger than the amount of water leaving this box, it's obvious that the water disappears somewhere. There's certainly there is a sink inside, or maybe sinks inside. So in the opposite situation, if flux out is less than flux in, it means that there are sinks inside, and divergence is negative. Negative divergence, it means that there are sinks inside. And finally, if this flux out is equal to flux in, it means that nothing disappears, nothing is being created, divergence is just a zero. So this is the main idea behind this test. Okay, let's get back. So now we were prepared with all these concepts. Let's get back to our example now. Let's analyze flux in and flux out. So as you can see, all the vectors have equal direction and equal length. It means that if you calculate the flux in is the collection of all these vectors times this area, this lilac area. But here you have the same situation. The vectors are the same. They have the same length. And the area of this side is the same. So it means that flux in is equal to flux out. It means that divergence of our field is zero. So divergence is zero in this case. You can move so this box acts like a metal detector. You can move it along the field, and you realize that you have the same situation everywhere at every point, wherever you move your test box. So divergence is zero for this case. Okay, it was a good beginning. Okay, now it's the second example is going to be much easier for you, because now you're familiar with this technique, this concept. Okay, the next field will be pretty similar, but you know what? The vectors are parallel to each other. So vectors are parallel to each other, but they have a tendency to become shorter and shorter if you move to the right. To the right. So what about divergence here? Okay, let's explore. We have our powerful metal detector, source detector, to be honest. Let's draw a box so that the two sides are parallel to our vectors. The reason why I didn't explain you the reason why we try to make two sides of this box parallel to vectors, because there's no flux through these sides, because the vectors, the fluid just passes by these sides, and it doesn't enter this box. It doesn't enter and doesn't leave this box. That is why it's recommended to make these two sides, opposite sides, parallel to vectors, because you will need to, after that, you will need to care only about in and out here, about front and back side. Okay, so let's get. Okay, so we place our detector here, and again, let it be the front side, it will be in, and this will be the back side of our box. Let's compare the fluxes. So what about flux in? Luckily, our detector has equal surfaces, equal areas of these surfaces, so we don't need to care about the area of these sides. They are equal. But as for vectors, you immediately realize, these vectors which are entering the box from this side, they are much longer than these ones. So as a result, the amount of water entering this box is much bigger, maybe just bigger than the amount of water leaving this box. How can this happen? It can happen if there is a sink here. Some amount of water should disappear inside this box. It means that divergence is negative. We managed to discover sinks here by our detector. Okay, Okay, so it's pretty clear. And of course, in the opposite situation, you will have, if these vectors were a little bit shorter than these ones, if there will be an opposite situation, you will have sources here. You will have sources. So it's pretty straightforward when you have these parallel vectors. But you know, things are much more complicated actually when you have these radial vectors. Look at this. So let's start with this point. So my vector, so this is like a central point of this field. So the vectors are coming from the center, and look at their tendency. They're becoming longer and longer. And the same with this vector, they're becoming longer and longer, and this one, and this one. So this is my vector field, and the obvious tendency is this: the farther you get away from the center, the longer your vectors become. Okay, so okay, I think that's enough because too many vectors will make my picture messy. Oh, maybe one more, like this, like this, like this. So, and you immediately get the impression that there must be a source here in the center of this picture. Yeah, maybe you're right, maybe you're not. You should be careful. The only way to find this divergence, to find these sources or things, is to use our test. And you remember, you need to use the box, but this time it will be curvilinear box, because the first rule you need to comply with is two sides of the box should coincide with your vectors. So let's take this vector and this vector. Look at this. So these sides will be like this, and your box will become curvilinear this time. So this will be the front. Again, this will be in, because vectors are coming inside the box, and this will be the outer surface. So, again, I'm repeating you once again. The reason why we choose these two sides, opposite sides, to be parallel to our vectors, so that we don't get any flux through these sides, because the vectors are just passing by, are sliding past these sides. This is why we don't need to worry about the flux through these surfaces. But as for these surfaces, it's time to analyze it. Look at this. Pretty obvious that the first area is actually smaller than the orange area. So this area, area 1, area in, is much smaller. Not much, but just smaller than area 2. We should be careful about it. So not only the length of the vectors should be taken into consideration, but also the areas, because flux is a product of all the vectors coming into this surface times this area. So we should be careful. But okay, let's see. Let's compare the lengths of the vectors. So these vectors coming in, they are shorter. They are short vectors. And vectors which are coming out, they are longer. This is the tendency of our field. What about the fluxes? So this lilac flux in is shortest vectors, all the shortest vectors times the area. And the red flux is this biggest area times biggest vectors. Of course, it's pretty obvious that flux in is smaller than flux out. Pretty obvious, because we are very lucky in these situations, because the vectors entering the box, they are smaller than these vectors, and at the same time even the area is smaller. The lilac area is smaller than the orange area. That is why the flux in is less than flux out. It means that that some amount of water is being created inside. It means that there are sources inside, and sources means that divergence is positive. Divergence of our field is positive. So because we discovered sources. And if you move this detection frame over to some other place, to some other spots, you will get the same tendency. So there's no point in doing this test several times. Okay, so it was pretty straightforward example, nothing fancy about it, even though it's quite an interesting idea about the flux. So the flux, remember that flux is all the vectors coming into this surface, in case of lilac surface, times area of the surface. And you need to compare not only vectors, the lengths and magnitudes of the vectors coming into this area and leaving this area, but also the surfaces, because they are multiplied by the areas of the surfaces. Okay, but the bad news is that actually this task is not always very straightforward. So this is what my fourth example is about. Let's consider again the pretty similar vector field, which has the source in the middle. And the vectors are coming out of this source, but this time they have a tendency to become shorter. So the first vector was long, this becomes shorter, shorter, and shorter with time. And let's plot several of them just for the convenience. They become shorter, shorter, and shorter. At first, looking at these vectors, you might get the impression, oh, this is the same vector field. You obviously have a source here. Like Sergey during the lecture compared the source with the kitchen sink. Do you remember? Probably if you look this lecture. Okay, but this time things are much more complicated. Let's make a test again. Let's make a test. Let's put our metal detector or source detector into this field and see what happens. So the first rule we need to apply to make this curvilinear box. I took these two vectors and plotted my sides, these sides parallel to these vectors. And this, again, this will be the in. Sorry. Just very strange sound. And this will be out surface. This will be out. And again, look at these areas this time. Okay, just like in the previous example, this lilac area, of course, is smaller than the orange area. So S1, S in is smaller than area out. Okay, no problem. Last time we were really lucky with it. But what about vectors? You know, vectors entering these areas, this area from this side, are much longer than vectors leaving this area. Why is this a problem? Let's compare two fluxes. Let's even write the formulas. So flux in, oh no, flux out, orange is flux out, and this is going to be flux in, lilac. Let's write the formulas for them. So flux out is like just vectors in, maybe. Oh, vectors out, sorry, I'm getting tired. Times area out. And this guy is equivalent to vectors in, all the vectors in, times area in. What can you say? Just compare these two terms. As for vectors, let me use, look at this. If you compare these guys, vectors out are smaller than vectors in, so the inequality will be this side, okay? But if you compare the areas of the surfaces, they have quite a different, quite an opposite inequality, because vectors out are smaller. Oh no, I made a mistake now, I think, somewhere. Areas. So area out is definitely bigger. So areas are bigger, and you can't. There's no way of knowing which one wins. Will it be the vectors who win and make the inequality direct in this way, or maybe these are areas which will win? In this case, you can't answer this question. You should put the answer mark here. So as you can see, this task is pretty difficult. Sometimes the case couldn't be straightforward, and it's quite acceptable that you can't resolve some of the situations just on the case. If you're really interested in this topic, and you should be interested, because it's expected that you are going to have these questions during the test or exams. That is why I recommend you to turn to Sergey lectures. He's going through these examples once again in his lecture. So, and he emphasized this idea that sometimes you just can't give the definite answer. You should put the question mark. Sometimes it's impossible to decide if the divergence is positive or negative or zero. So that's it. This tutorial is finished at last. 2 hours, almost 2 hours. The five, what is the scalar field? What do you mean? I didn't quite understand. Can be a scalar field. Oh, what do you mean? What do you mean? To be honest, I didn't quite understand your question. The very first page. Oh, Where is it? This page? I think that it's better for you to watch this tutorial once again. What about the first page? There were 5 scalar. Not rules, but 5 topics. I just wanted to give you the layout of this course, and the layout of this tutorial at the same time. I'm trying to find this paper, this page, and I can't. So many papers now. My gosh, I can't. I think I missed one. Really? But you can watch this tutorial from the very beginning, no problem. I think that I mentioned everywhere, everything there. I can't find it. My goodness. Yeah. I found this page. You mean this page? Yeah. So, I think that gradient, directional derivative, maximum change of rate, normal vector. I forgot to mention the first topic, which was contour plots, probably. That is why this numbering is not very, representative. Okay, it's not a problem. Actually, I explained everything to you which I wanted to. Okay, so that's it. This tutorial is finished at last. Okay, yeah, you're welcome. You're welcome. Okay, so see you next week then. Okay, bye-bye. So I stop recording now and I'm leaving this tutorial. Okay, bye-bye. Bye-bye.